Good morning, everybody. I believe we are live. So today, this is the continuation of the dynamic programming line. This is part 4. We have solved a lot of medium problems. We have solved some subset-based problems, some recursion, some other stuff. If you watched that, great. If you have not watched that, try to watch them. Uh, Today, we want to have a bird's eye view of whatever we have learned. Maybe revise some of the concepts, revise divide and conquer strategy, and how to think about the dynamic programming problems, how to think about basically how to think about just divide and conquer. So this is what we will focus on because this technique is kind of very beneficial for solving advanced level dynamic programming problems. Like we have solved problems based on peak, non-peak, maybe some recursion, maybe try to think of them as some recurrence. So we will just dive deeper into that. Yes, initially we will be solving some easy problems, like maybe sum of elements in an array. But we really want to make our thinking of divide and conquer stronger. Okay, that's what we want to do. Let's see. Let's see. We are live. Yeah, I think we are. This is good. So that's our primary objective from this session. So let's think of the first problem. That is sum of elements in a given. So, of course, there's a very easy way to do this, but again, we want to use divide and conquer. So maybe if this is the element given to you, 1, 5, 6, 3, 4, 3, 9, 7. We want to split it into two halves. Maybe 1, 5, 6, 3, and 4, 2, 9, 7. This is how we want to partition. Maybe this partition again. Okay. So I want you to think of this and maybe write down a code that probably solves this. So try. Yes, give it 10 minutes. Maybe try to implement a solution to this problem. Sum of elements in a given array, so divide and conquer. I hope you have spent enough time on this problem. So let me give you the solution for this problem. Just go look at the folder. Mm, Let's say this is problem one. We will be dealing with normal templates only because you're you've already covered a lot of template stuff. Okay. So let's say we're given an integer array of size n. This is everything is visible. It is. So let's say the size array is given. And now we see that we return the sum, right? So we will try to define the sum. So we have to sum which is some function taking some L and some integer R. And also itself. We have to return an integer. So I will say if L is greater than or L is greater than R, return 0 L1. So I think I should return long one because some is. And if L equal to R, return P of R. Otherwise, return is some function being called from L to mid plus some function being called mid plus 1 to R. Where mid is L plus R minus L divided by 2. I hope that makes sense. L to mid, and of course I should pass myself. Okay. In the end, we will call this function. Maybe I will call this function. So maybe sum from 0 to n minus 1. So give me something. Let's print that out with a line break, of course. Please don't worry about the implementation details or the stuff here. Okay. Okay, the sum is a bad word. Maybe let's name this. I think I should name this. I think it will not work still, as long as the function definition is okay. Hmm. Let's not call this sum. Maybe if sum. That should work, I guess. Yeah. So maybe a 5, 6 is maybe a 4, 3, let's say a 7 size array. 1, 5, 6, 7, 2, 1, minus 6. Okay. So 1, 2, 3, 4, 5, 6, 7. It should work, I guess. So it's not giving the sum of it. If L is greater than R, then 0 is equal to R. So 2, then 1, so okay, it's working. It's with 7, and let's say 1, 5, 6, 7, 2, 1, minus 6. It's 16. This is sum 16. I think yes. I don't know why this one is failing for some reason. Yeah, it's giving 16 now. I hope this is clear. Now, I think we have already solved the problem of Fibonacci. Maybe try giving it 10 minutes more. Maybe try to prove that why memoization in Fibonacci is important. How the answer changes, or like try to count the number of function calls made on memoization and not on memoization. Try to prove that how memoization helps. Maybe use a functional counter as soon as you enter a function. Maybe increment some variable to prove that if Fibonacci of let's say 15 you want to calculate, how many times I've entered the function, provided I have not used memoization. And also another function that is memoized. Try to calculate the number of times I have entered the function, use it, and see that there is a huge difference, like 2 to the power n and 1 is order n. Try to prove that or show at least that how these vary. Okay, so let me write down the question for you. The next problem is problem 2. Show by counting function calls how Fibonacci Fibonacci uh, mm, takes much less time by of course less function calls on memorization. Okay, this is the second question. I want you to give at least 10 minutes. Sure. Okay. Okay, so I think we have given enough time to solve this. Let me just give you the solution now. So let me just say go to problem 2. So p2.cpp. So we want to prove that the Fibonacci actually takes less time, like through amount of function calls. So let's try to define our usual Fibonacci function. So I can say, so it's an int n is given as input, and I want to calculate the nth Fibonacci number. So of course we can just define the preview function, right? And that will take parameter n. For that I want the nth Fibonacci number. Of course the return type can be long because it can get very big. Of course, if n is greater than equal to or less than equal to 1, we return 1. Otherwise, we return the same idea n minus 1 and but we want to prove that this function on being executed takes a lot of time, right? So maybe use this function definition since we don't want to carry references, right? Return type is ln and the type is integer. So this kind of helps. So now let's say I define a variable enter equal to 0. And every time I enter a function, so I can say entered plus plus. So we will try to calculate. So print and then feed of this n. And after printing this, I also want to print that number of times I have entered my function, right? So let's try to test it out for some big value, maybe 20. Of course, I'm selecting smaller numbers because Fibonacci has complexity 2 to the power n, and 2 to the power 20 is very high. So you see, I have the answer is around 10,000 something, and I have entered the function 20,000 times for just a value of 20. If I set 30, then like it is not even double of 30 or triple of 30 or square of 30. It's very high. For example, it's 2,69,000, or let's say I think this is, I guess, very high. So it's like 10 to the power 1, 2, 3, 4. It's order of 10 to the power 6 for just the value n equal to 30. So very high. So this is the way we can prove that Fibonacci takes very high time when memoization is not used. Now we will try to maybe replicate this. So we fib2, but this fib2 will be using memoization, right? Of course, before going to fib2, we will just say that let entered equal to 0 because, and now we will not be using this fib2 fib n minus 2. We will specify. So maybe use a array that can be used to store the numbers. So VLN answer, of course, that has to be size n plus 1. And initially we can have a default value of minus 1. Or we can have a separate visited array as well. If you cannot figure out what can the default value be, which can never be the answer. So in this case, we know that minus 1 can never be the answer. So we can initialize it as minus 1. Now, of course, we will just one memoization step before returning and answer of This particular level is this, and we check if answer of n is not equal to -1, I return answer of n. So again, I will be calling this fit2 of n. So let me just maybe put some, uh, let's put memoirs. Okay, and here we can print uh, bare metal or not memoirs. Okay, let's try to run. You see, if we had not memoirs, the answers are same in both cases, but in the other case, you see, I have only entered the function 59 number of times. So only twice the, let's say take a very big number. Of course, in that case, this will fail. Maybe take 100. So 2 to the power 100, I think it will fail. It will take a lot of time actually. Yeah, I think I have a 15-second timer. So if it takes more than 15 seconds, it will break automatically. So no, it is timed out. So maybe let's try 35. This is still very high, but I think this will run at least. Yeah. So you see that it is still only 69 number of calls and not memoized. The function call has entered way too many numbers. It's almost as 2 to the power 35. Let's try to calculate. We have a calculator. No, let's try to calculate 2 to the power. So let's we can calculate it about 2 to the power 35. It's approximately around this number. Okay. Of course, the answers in both cases are same. So this is the solution to the problem. How to prove that actually memoization helps in any dynamic programming based situation. Of course, you can make a graph or direct acyclic graph in order to show that it works. Okay, let me give you the third problem. Assume, yeah, assume that problem 3. So problem 3 says, given n cross n grid containing some values, so find out minimum cost path from 0, 0 to n minus 1, n minus 1. Of course, this is in zero-based indexing. In one-based indexing, it will be from 1, 1 to n. So basically, I want to go from here to here, and and every cell contains some value, say 5, 3, 2, 6, 9, 7, -1, -2, -3, 4, 7, 1, 3, 2. So it contains some values. Dot, 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 dot. I want to go from point A to point B, and every cell has some associated cost that if you step on that cell, you have to pay the fare. So try to solve this problem. I think my previous lectures of GP Grind 1.3 should be cool. Try for 5 minutes, and then we discuss. Okay, this is the problem 3. Let me just start solving the problem. This is problem number 3. CP3, CPT. So let's say we are given a name. Now we try to determine the minimum cost path from 0, 0. So it's like my answer is println my some function that's recurrence of 0, 0. It should work. Of course, I should pass self because I'm writing combinator based. I should say recursive lambda function. So the auto rec int I j. So of course, if this uh, I is greater than or equal to n or j greater than or equal to n, we return into max because I want minimum cost path. So that can be considered as the default express. Of course, I should be passing this to self as well. Okay, this is understood. Now, also we have to consider the left move and the right move and the down move. So I return the minimum of that. So return minimum of this rect being called for I plus 1 j and this rect being called, or I should say self being called, with self present, and the self also being called for I and j plus 1, with self also being present, and that should be all. It is expecting some. Okay. Hmm. Expected a semicolon recurrence of 0, 0. Okay, so this will be recurrence first. Okay. So maybe LL max, but still, if R is greater than N or J greater than N, then that otherwise return should say G of IJ plus this one. I don't understand why this was not correctly. Print if result equal to. Okay, okay, sorry. Put a semicolon here in order to end the function, right? Because this is a recursive solution. I have to memorize this. So how can we memorize? We can just define a 2D grid. So DP. Of course, we can initialize everything as long max. Mm, I think this should be m comma long max. Okay. And now before returning, this is a TP of ij. equal to my thing. I think better if we just use a visited array. So maybe not this. It is more elegant, better, I should say. So visited array. I think the Boolean is enough. So initially by default it is false. Return dp of ij equal to, of course before, so I should say uh, so visited of ij equal to 1. And of course if visited of ij equal to 1, then return from dp of ij. I think this does it. Let's try to print for a small grid, maybe 3 by 3 grid. Let me put some values, some common values. I think I have it saved. So 158, 627, 167, 628, and maybe 917. And minus 2. Okay, I think I have to enter this G as well. Otherwise, the answer will be 0. Yeah, okay, I think I have done some mistake. If R is greater than or equal to N or G, N with a lot of max, if it is equal, then I can just put on otherwise G of IG plus mu. Um, why is it negative for some reason? Int max. It is returning int max. Okay, let's think. We may have done some silly mistake. Mm, here I have- let's think int max. If it is 1. Mm, I think I have not defined base cases, right? Yeah. So if I've reached my destination, if I reached my destination, if I equal to n minus 1 and j equal to n minus 1, I just return this g of ij as the value. Otherwise, it will always go up to the boundary. Yeah, it is 8. So I think 1, then 6, 7, 8, 9, 10, and 10 minus 2, 8. This is probably the optimal. If you just redefine my variable, yeah, I hope this problem is understood. The next problem that we are going to solve together is given an array of integers, uh, try to pick a subsequence of elements such that we do not pick any two adjacent elements and the sum of picked elements are maximized. So let me write down the problem statement for you. This is kind of like the house order situation, if you remember. But we are trying to give have a Codeforces kind of problem solving aptitude on this. So this is problem 4, right? Yeah. So let's say given an array of some integers, pick a subsequence such that sum is maximized, but cannot be adjacent elements. So it's like what? Yeah, I think the problem statement is enough. Given some integers, of course, positive, negative, both can be present. Otherwise, if all of them are negative, we will not pick anything. If all of them are positive, we will just try to pick. Still, uh, try to pick a subsequence so that the sum is maximized. Of course, I have to give you some idea that n is up to 10 to the power 5, and of course, a of I is up to 10 to the power 9. So maybe try for 10 minutes. Okay, sorry. Uh, Now let's try to solve this problem. This problem we will solve through four different approaches. And by these four different approaches, I will try to explain how to define a state and how the transition equations change based on the definition of states. So we will try to define our problem or the answers to some problems in four different ways. And we will try to give, knowing that this sub-problem's answer exists, how we can transition from it and how that will change based on the definition of my problem. So let's go back to the picture. So P4. So first we have an array. Now I want the maximum sum and I cannot pick adjacent elements. Now we will try to define our problem in four different ways. So let's say way one. In way one, I will say let's define dp of I equals to max sum from 0 to I, such that I don't pick adjacent elements. So I already know, or I have already defined that the dp of I will be the maximum sum I can conjure up, considering the elements from 0 to I only. Okay, so if this is understood, can I say that that means the base case 0 has to be defined? So it's like that means dp of 0 must be max of 0 comma v of 0. Since 0 to I am considering them, so 0 to 0 I must know, or and 0 to 1 I should know, right? So like 0 to 0 is just kind of the smallest problem. If 0 to I is my area of research, now how to define transition. So this can be the base case. Okay, transition can be, so 0 to I have defined, right? So can I say that dp of I equal to max of either I pick up the ith element or I do not pick up. So I can say dp of I is to max. So I have two ideas. Either I pick up the ith element, so v of I plus dp of I minus 2, or I do not pick up dp of I minus 1. This is my transition equation. So either I decide to pick up this ith element, that means I can only consider elements from dp of I minus 2 to 0 or 0 to I minus 2. From that, we will try to conjure up something. Otherwise, I will decide not to pick up this element and consider only the elements from 0 to I minus 1. Of course, dp of 1 I have to also define. It says max of dp of 0, and either to consider that or not consider, and maybe max of v of 1 comma 0. Maybe, maybe consider, because there is an I minus 2 here. So do I really want to consider the first element? The answer from 0 to 1 is either you pick up the 0th element or you pick up the first element. I can say that dp of uh, 1 can be max of 0 comma v0 and v1. You can only pick up one from those or none from those. That's the way. So this can be defined as way number 1. Let's try to define way number 2. Here we will define maximum sum from I to n minus 1 such that I don't pick any adjacent elements. Of course, everything will change based on the definition. So I to n minus 1. So that means my smallest problem is n minus 1 to n minus 1. So can I have to mention that dp of n minus 1 equal to max of n minus 1 or max of v of n minus 1. If I have to consider that or not consider that. And of course, I have to pull it up. So maybe if I want to consider the ith element, so dp of I equal to max of two cases. If I'm considering the ith element, so v of I plus dp of I plus 2, otherwise dp of I plus 1. These are the two cases. Of course, if there are more than, if there are two elements, I have to say that dp of n minus 2 should be defined as max of 0 comma v of n minus 1 comma v of n minus 2. Just taking care of bounds. Okay. Now, this is the way number 2. Let's try to define a third way. Of course, I will be implementing my solution for all of these ways. So, if you are finding it difficult, maybe pause for some time and maybe think about why these transition equations will work, how I am thinking about as I am writing these transition equations, how it is defined, like I to n minus 1, right? Okay, so way 3 can be, of course, now I will not consider it directly. Let's say it's seen it in some books that dp of I 0 means is the maximum sum from 0 to I such that I do not pick up ith element. So I've defined that I'm definitely not picking up this ith element. Of course, that means I will not have two options in this max function, right? So since I'm dead set on the idea that I will not be picking up this ith element, so can I say that dp of I 0 means, since 0 to I am considering, so dp of I minus 2. But again, 0 to I am considering. So, and dp of I minus 2, should that have the parameter 0 or 1? Possible. So maybe max of this being 0 or 1. What about dp of I1? That means I have decided to pick up this ith element. I think since I'm not deciding to pick this up, so maybe dp of I minus 1 that I can pick up or not pick up. And dp of I minus 1, since I am decided to pick up this ith element, so it should be v of I plus dp of I minus 2. But should I pick this one? That is my question. Like, say that I have decided to pick this up. So it's like I0 can be I minus 1, 1 or 0. And if I have decided to pick up this ith element, I think I should say that, okay, let's not go back I minus 2. I can say that I minus 1, I'm definitely not picking up. Because I minus 2, I don't know. So I'm thinking like, so dp of I0 means the maximum sum I can make from 0 to I so that I do not pick up the ith element. And dp of I1, that means that maximum sum from 0 to I, so that I definitely pick up the ith element. Now, if I'm not picking up this ith element, I have option that I want to pick up the ith element, I minus 1 element or not. But if I've decided to pick this up definitely, then I get this to my answer. And I'm sure that I minus 1 I must have not picked up. Or the answer from I minus 1 such that I have not picked I minus 1 is guaranteed. Right? Of course, I have to say that my final answer will be dp of 0 to I. So it should be n minus 1, n minus 1, 0, max of, or n minus 1, 1. Because the last one I may pick, I may not pick. I want the maximum of both of those. So this was the third way. Of course, you may have guessed by now what will be the fourth way. It's like the same thing, but instead of saying that dp of I is the maximum from 0 to I will say it's the maximum from I to n minus 1, such that I do not pick up ith element on dp of I1, that is, I pick up. Okay, that means I0 is defined as I have not picked up this ith element. So I plus 1 will have choice. And not picked up, so I plus 1 will not have choice. And in the end, I will say that dp of 0, 0, that's my final 0th element I can decide to pick or not decide to. It's I to n minus 1. So my final answer is 0 to n minus 1, provided I may pick up the 0th element or not. So this will be way 4. Okay. So let's try to implement this to all these ideas. I want you to understand how these ideas are working, how I have modified my transition based on this push idea or the pull idea of DP, and maybe building up the solution. Okay. Okay. So let's try to implement now. Uh, so this is V5. So let's go let's take the input first. So int n, was it P4 or yes, it was P4 only. Sorry. So we have taken in the input. Uh, Now let's try to discuss way one. In way one, we have defined GP of I is the maximum sum from 0 to I, such that this, otherwise that. Now you understand, since I am only depending on I minus 1 and I minus 2, I can start from 0 and maybe work our way up. So let's define dp of 0 and dp of 1. So if n equal to 1, return d of 0, or I should say max of v0, comma 0. We have defined this one size separately. Okay. I think I should print and then maybe after printing return. Now let's discuss way one. So I know at least two elements are there. So I've defined some base cases. So dp of, since I have defined from 0 to I, so I've defined dp of 0. That's the smallest problem. So dp of 0, of course I have to define this dp. So dpll dp way 1. Let's say dp1 because way 1 I want to say equal to, so I think n plus 1 size we work. So dp of 0 equal to max of v0 and 0, and dp of 1 equal to max of 0, comma v of 1, comma v of 0. That's how we have defined. I think this will be 0 error like this. I think I should say dp1. So we have kind of defined our base cases. Now we want to, since we are only dependent on I minus 2 plus 1, so maybe start from second. So ff forward loop I from 2 to n minus 1. I just write down the equations. So dp of I equal to max of dp of, or v of I plus dp of I minus 2, and dp of I minus 1. And in the end, we just say that, of course, not dp, I should say dp1. And in the end, we print dp of n minus 1. I think that was a solution. Yeah, 0 to n minus 1 was our solution. So this was the first way. I don't think I need brackets for this. Now let's go to way 2. Here also, we have to define n minus 1 and n minus 2. So this will be n minus 1. Here this will be n minus 1 and n minus 2. So we have defined the base cases. Now we will reverse the loop. So for fr reverse from, I can say n minus 2, so n minus 1. I think I should start from n minus 3 now. And I will go up to 0. And I will check that dp of n minus 1 will be max of, yeah, that is n minus, dp of I should be v of I plus dp of I plus 2, v of I plus dp. I think I should say dp2, dp of I plus 2 or I plus 1. And in the end, we can just print dp2 of 0. I think this should work. So this was way number 2. Way 3 is a little bit different. Uh, Here we have defined our state 2D. So VLN, so VLL and maybe 2. So here we have defined that set dp of, I think we have defined that is the maximum sum from 0 to I, such that I do not pick up the ith element. Okay. So I have to mention that what is the value of dp00, right? So dp3, I should say. I have to say that dp3 of 00, I have to mention that if I do not pick up the 0th element, it will be nothing. If I pick up the 0th element, it will be dp of 00. I mean dp of 0. If I decide to pick up the first element, then it should be dp of 1. If I, of course, if I decide not to pick up the first element, then yes, I think I should say dp3. No, sorry, it's Z. So it's like if I've decided not to pick up the first element, the answer should be 0. If I've decided to pick up the first element, then the answer should be B0. Now, for the first element, if I've decided to not pick up, the answer can be so max of TP of. I think I do not need to mention this one idea because, anyways, I'm not dependent on two cases. Only I minus 1 I'm dependent on. So I can maybe start from directly 1 and go up to n minus 1. So only these two definitions is enough. So dp3 of I and 0, if I've decided not to pick up this ith element, that means I can either go dp3 of I minus 1 of 0 or I minus 1 of 1 if I've decided not to pick up. If I've decided to pick up, then it should be dp3 of I1, it should be And since I decided to pick up, so it should be V1 or VI plus my DP3 I minus 1, which I have not picked up. And in the end, we want to say that since 0 to I is defined, so maybe n minus 1 being picked up or 3, I think so, n minus 1 not being picked up. And I want the maximum of those. So this was the way number 3. Way 4 would be the same idea, but again, here we have to mention that n minus 1 and n minus 1 being 0 or n minus 1. If it is picked up, then it should be v of n minus 1. Here it will be a reversed loop from n minus 2 to 0. Here we will say, I think I should say this is dp4. Here I'm saying that if I decided not to pick up this ith element, I can either go +1 and maybe pick up or not pick up. Otherwise, I cannot definitely pick up. And in the end, I want the answer for 0, 0 or for the 0th element being picked up or 0th element not being picked up. So let's try to run this. We'll get 4 different answers. I am expecting all 4 to be the same. Let's try to have an array. I think I have it noted down. So 1, 4, 2. So 1. So maybe a 5 size array. 1, 5, 2, and then minus, let's say minus 8, and then let's say 11, and let's say a 5. I hope that I have not done any silly mistake. Okay, comp cannot be used. Uh, where is it being affected? 306. Line number 20. Yes, base test to be C++. Cannot compare long. Maybe some comparison error. Maybe 0 LL. You can just normally use 0. Uh, yeah, I think 0 LL is required. Already compare. Will it work now? Okay. Uh, 257. it's causing here, so maybe 0 ln small. I don't think that is helpful. Okay, I think I should do here third bracket so that it can compare three values at least. I don't think it's expecting three arguments directly, is it? That also means that I have a problem here. Yeah, it's expect 265. Yeah. If I have to give three arguments, I have to put them in third bracket or curly brace. Yeah, so 15, 15, 15, 15. So all of the four approaches have given the same answer. Let's check for another test case that is again 5 size. I think 1, 4, 4, 2, and then minus 10, and then a 10 and a 5. The expected answer is around 13. Oh, exactly 13. It's 14, 1, 4, 2, minus 10, 5. Can I create some 13? So 1 plus 2, 3. Yeah, I think the answer should be 14 because that's the maximum sum I can make. 13 I can also make, but 14 is the maximal. If I have to pick 4 and 10, so to be optimal, not to choose the adjacent elements. Yeah, the answer should be 14. I hope you understood this problem. Try to go through. This notes will be available in the description. Uh, what is it? So notes will be available in the description. I hope you try to understand this four approaches. Implementation details will again be in the description. It will be a GitHub repository. Uh, we learned about some concepts here. We learned about transition states, how to think about transition and states in one dimensional and a little bit of two dimension, just Boolean double variable, 0, 1. We've learned about how definition of problem is so much important and how definition kind of changes the transition that we want to impose. This should be n minus 1, comma 0. I hope this is understandable. Let's see how long the stream is running. It's around 1 hour 35 minutes. Have a great day. Uh, all of these codes, along with the notes, will be available in the description as a GitHub repository. Thank you very much for watching. You can support me. The details are in the description if you find value in this channel. Otherwise, thank you very much. Again, like, share, subscribe if you find value, and have a great day. Good morning, everybody. Like this morning here, if here, like if it is good night, evening, good evening, afternoon, then good afternoon, uh, whichever app is applicable to you. Anyways, as a general, have a great day, and thank you very much for watching. Goodbye. Until next time.